Let ABCD be a cyclic quadrilateral. Let E and F be variable points on the sides AB and CD respectively, such that AE over EB is equal to CF over FD. Let P be the point on the segment EF such that PE over PF is equal to AB over CD. Prove that the ratio between the areas of triangles APD and BPC do not depend on the choice of E and F. So the first thing we need to do is find out how we're going to find out the area of APD in the first place. And we have this point P in the middle here that is expressed in terms of E and F and the side lengths AB and CD. So in fact, we can express the area of APD as a function of the area of AED and the area of AFD. So that in particular, APD is equal to some constant times the area of AED plus another constant times the area of AFD. And in this case, we need to weigh E a bit more because AB is less than CD in this case. So in order to weigh E a bit more, it makes sense that we need to multiply by CD because it's a linear function. So we multiply by CD and then AB and divide everything by AB plus CD to balance things out. Now the question is, how do we find out the area of AED and AFD? At this point, we now need to use this fact over here. We could set this common ratio to be something like k, where k is some real number. And so in particular, we set AE over EB is equal to k. Then this obviously means that AE over AB is equal to k over k plus 1. And similarly, DF over FC, or DC on that matter, is equal to 1 over k plus 1. So therefore, this means that the area of AED is equal to k times the area of ABD over k plus 1. And similarly, the area of AFD is equal to the area of ACD over k plus 1. And now plugging into this equation, we end up getting that the area of APD is equal to getting rid of the factor of k plus 1 and factoring it out. We get 1 over like A plus B, AB plus CD times k plus 1 times this huge expression here. CD times KABD plus AB times the area of ACD. And we don't need to do the exact same computation again for the area of BPC, because we can just repeat the argument. Doing so, we end up getting that the area of BPC is equal to 1 over this big constant on the bottom times AB times K times the area of, and over here we have that is BCD plus CD times the area here of ABC. And now we just need to take the ratio between these two and show that as constant. All right, so now and after we divide this entire thing, we get that this ratio here, because this constant cancels out, is equal to this big thing here. And we want to show that this is independent of k. So from what we know about ratios, this is equivalent to showing that AB over CD times ACD over ABC is equal to CD times ABD over AB times BCD. And now that we have cyclic quadrilaterals here, we can express ABD in terms of the sine area formula. So we have that AB times the area of ACD here is AD times DC times the sine of angle ADC. So it's over here 80 times DC sine of angle ADC. And then this is CD times AB times BC times the sine of angle ABC. And conveniently, the AB and CDs cancel out here. And we want to show that this is equal to CD times the area of ABD here is equal to AB times AD times the sine of angle BAD. And on the bottom here, we have AB times BC times CD sine of angle BCD. And conveniently, we also have the AD. The AB and CD cancel out here. And we have an AD and BC on both sides, so those can go away. So now we just need to show that this relationship holds here. The sine of ADC over the sine of ABC is equal to the sine of BAD over the sine of BCD. And now we just note that each of these areas is just equal to, each of these is equal to 1 because each pair of opposite angles add to 180 degrees. So therefore, this vanishes, and so does this. And we are done. We have shown that these areas, that the ratio between the areas of APD and BPC is independent of K. And we have solved the problem. So thank you so much for watching this video. Please subscribe if you'd like to see more.